In an occupied space in a cold climate, heat will flow out. This is a heat loss. If the indoor and outdoor temperature are the same, no heat will flow. There is neither heat loss from the space nor heat gain into it. When it is hot outside, heat flows from the hotter outdoor air into the cooler indoor air. This is a heat gain. Likewise, if the temperature of the air which passes over the coil is higher than that of the refrigerant in the coil tubes, heat will flow from the air into the refrigerant. The coil, in this case, provides cooling capacity. If the refrigerant temperature is equal to that of the air flowing over the coil, there is no heat transfer and therefore no capacity provided by the coil. If the air temperature is lower than that of the refrigerant in the coil tubes, heat will flow from the refrigerant inside the coil to the air moving over the coil. Since the air is heated, we can say that the coil provides heating capacity in this situation. There are three different means by which heat flows. All three play a part in mechanical refrigeration and work together to make heat transfer happen. Heat is transferred by conduction, convection, and radiation. We'll look more closely at each of these by first defining the term and then by viewing each method as it occurs in three settings. First, in nature; second, as it appears in a space as load; and finally, as it applies to equipment as capacity. In nature, we don't see the forms neatly separated. They are generally mixed together. Conduction is the transfer of heat from molecule to molecule through a substance by chain collision. Heat added at one place causes the temperature of the substance being heated to go up because the molecules move about more rapidly. These high-velocity molecules start a chain collision with molecules near them. The chain reaction moves throughout the material. While conduction takes place in gases and liquids, it works best when molecules are closely packed, as they are in solids. If one end is kept in a flame, conduction eventually will cause an iron bar to become too hot to hold. Conduction through roofs, walls, windows, and doors is what allows heat to enter a tightly sealed house as cooling load. Conduction is also what allows a cooling coil to provide capacity to cool the air. Heat from the air moves into the cold refrigerant by being conducted through the tubes and fins of the cooling coil. Convection is heat transfer by the movement or flow of molecules from one place to another. Heated molecules within a flowing medium, such as air, carry their heat directly to a new area. In a forced air heating system, for example, air flowing through the conditioned space carries heat by convection. Convection currents are easy to see in a pan of water being heated on a stove, especially just before boiling begins. Natural convection currents, like these, are also called density currents because their movement is caused by differences in fluid density, which are a result of temperature differences. Less dense fluids tend to rise, while more dense fluids fall. In cold climates, convection causes heavy cold air to form a downdraft off outside walls and especially windows. As new air rushes in behind that which falls off the windows, heat is transferred from above the windows down to the window where it becomes a heat loss for the space. In this case, convection causes discomfort because of the cold puddle of air which builds up on the floor. Convection can also be at work as heating capacity when a baseboard heater is installed below a cold window. The less dense heated air moves upward, taking heating capacity to the load at the window, wall, and ceiling. As the air molecules lose their heat energy, they become colder and more dense, falling toward the floor. Cold air moves into the heater to make up for the warm air moving up, which solves the downdraft and cold puddle problem. Radiation is the most common and least understood method of heat transfer. Most common because most of the heat energy of our planet comes from solar radiation. Least understood because radiant heat can't be defined in terms of colliding and moving molecules. Radiant heat usually behaves as a wave form of energy, but also possesses some qualities of energized moving particles. Radiant heat has the ability to pass from one place to another without heating up the area in between. For example, a camper sitting in front of a fire on a cold night can get warmed even though the air between him and the fire remains cold. Also, radiant heat can only heat what it hits. The camper's front side is warmed, but his back remains cold. Radiant heat can only heat materials into which it is absorbed. The camper will get warmest by wearing dull black clothing and will remain coldest by wearing reflective clothing, other things being equal. This is why people in hot, sunny climates tend to wear white clothing. White is a good reflector of the sun's radiant heat energy. Solar radiation comes through windows in a building, strikes walls, floors, furniture, and people, and is absorbed by them. As it is absorbed, it heats up the space and becomes a cooling load which may need to be removed by cooling equipment. Radiant heat is sometimes used to provide heating capacity from overhead as a method of warming people or products without heating the air in between or the entire area. Radiant heat is almost always seen in combination with other forms. Heat transfer can be greatly affected by the materials selected in constructing buildings and heat transfer equipment. Conduction, convection, and radiation are all affected by these materials, but we will focus our attention on conduction because it affects us in a major way in refrigeration load and equipment. Materials which help heat move by conduction are called conductors. Those which retard it are called insulators. Good insulators make poor conductors, and vice versa. We use good conductors when we want heat to be transferred. We use good insulators when we want heat to stay where it is. For example, we put fiberglass insulation in our attics to help keep heat from escaping. As a general rule, materials that conduct electricity well will also be good thermal conductors. Metals are good conductors. Silver and gold are excellent, but are not very practical for use in heating and refrigeration equipment. Copper is nearly as good a conductor as silver and has the advantage of being much less expensive. Aluminum, among other common metals, is also an excellent and relatively inexpensive conductor. That's one reason most heat transfer coils are made of copper tubes with aluminum fins. This arrangement speeds heat transfer from the air into the refrigerant within the cooling coil or from the fluid within a heating coil into the air flowing over it. Since copper and aluminum tend to melt under intense heat, steel or cast iron is often used for heat exchangers on direct-fired heating equipment like the furnace shown here. A good conductor speeds the heat transfer from the flame to the air flowing over the outside of the heat exchanger. Trapped air is one of the very best insulators available. Examples include expanded polystyrene foam board, fiberglass and cellulose insulation, and dead air spaces, such as those found between the panes of a double glass window. Corkboard and wood products, especially softwoods, are also good insulators.
We are committed to sharing knowledge and helping everyone improve their professional skills. If you enjoy this type of training, please like this video and subscribe to the channel. The next episode will be even more exciting, so don't miss it. You are also welcome to leave your comments or email us with the topics you are interested in. We will select the most requested topics and discuss them in future episodes.